Zaifa, can you hear me?
Oh, sorry. Radu, I can hear you.
You can hear me? Okay, good.
Yep. Okay. So I just opened it in YouTube, but so this is what we'll be trying to do today. We have this Python script, this is PyChrono, and we'll be trying to launch it from the terminal and simulate this vehicle. And this is real-time runtime visualization. So this is how fast the code runs, if you're curious. And then the vehicle brakes, and I cut the simulation so it doesn't fall off. It does. Okay. Wrong slides.
This lecture is an introduction to time domain and frequency domain. It's easy to see the physical.
Sorry about that autoplay. Okay, so that will be our end goal. Great. Okay, so that will be our end goal, the simulation you just saw. So a little bit of introduction of fluid structure interaction and the different ways to do it. We actually offer two ways in Chrono. One is a monolithic approach. It's called the constrained fluid formulation.
You're not sharing slides.
And it's only implemented when you use your multi-body system in a non-smooth contact setting. You don't need to know that for now, but there's just one constraint. And what happens in this is you treat the fluid as a set of constraints for your multi-body system. So you know that the fluid is incompressible, and the incompressibility constraint is an algebraic constraint which you can define. And you know that the fluid cannot penetrate into the rigid body. So you can define these non-penetration constraints through complementarity conditions. And you can solve this big system of equations with constraints. It turns out to be like a differential variational inequality problem. But then it's a big matrix problem. You use optimizers and all of that stuff, which is like how Chrono works. But this is one approach where your fluid is like within like the multi-body system almost. So that's why it's a monolithic approach. The other approach is the partitioned approach, where you use another way to discretize your fluid domain and solve the partial differential equation of the fluid directly on the computer, and you kind of couple it with your multi-body system. So to your multi-body system, the fluid is just some sort of external forces, and to your fluid system, the multi-body system is just some rigid bodies whose positions and velocities have been set. This is like a partitioned approach, and as I said, there is like a force displacement coupling. We'll talk about that and how we do that physics. And also this allows for doing the fluid, which is like a higher dimensional problem because you're discretizing space. And so there are a lot of degrees of freedom that turn up. And so you can do that on the GPU and communicate the forces from the fluid domain back on the CPU. So it allows for this partition in the hardware as well, not just the physics. So you can efficiently simulate both the fluid and the multi-body dynamics. For this lecture, we'll be focusing on option 2. So I'll be talking about the partitioned approach and how you can set up a simulation using this. Okay, so a little bit more about the partitioned approach. Okay. So as I said, it's an explicit force displacement co-simulation framework. That's a big term, but what it basically means is you have your solid dynamics. This can be rigid bodies, flexible bodies with FEA. You can have smooth contact, non-smooth contact, and this runs on a CPU. It can be with OpenMB. You can do multi-core processing for this system as well. And then you have your fluid domain, which we use SPH as a numerical method. We'll talk about that. Yeah, but
Huzaifa, can you hear me?
Okay, sorry. Okay. So yeah, we'll talk about that a bit. the SPH part, but you have the solid part that you solve separately. You have the SPH part that you solve separately, and you communicate information back and forth. So from the fluid part, you get like your force. So the fluid exerts a force on the bodies. The bodies take that force and do its dynamics. And then the bodies come up with like, oh wait, because of this force, I'm now in this position. You communicate that information back to the fluid, and then the fluid uses that to do its thing. So this is how we communicate information back and forth. In this partitioned approach. Okay, so a little bit about the structure of like in Chrono, how this is implemented. The main idea of implementing it this way is that you could use any hydrodynamic solver for the fluid. What I mean by that is you need something that exerts a force on the multi-body dynamic system. It could be SPH, it could be your own hydrodynamic solver, it could be another version of SPH that you prefer. You could just plug that in to the class structure in Chrono and use your own SPH or use your own hydrodynamic solver. We in Chrono provide Chrono SPH, which is one instance of that hydrodynamic solver. So we choose to provide fluid forces through SPH, and we have an implementation of SPH, and this is what is the bottom box here. So we have these systems, CH fluid system SPH, which we have some utility classes that help set up the system easily, not of much importance, but you just need to understand that we have this CH fluid system SPH that does the SPH portion of the fluid structure interaction or the fluid portion of the fluid structure interaction. And if you would like, you can define your own CH FSI system SPH, plug it in, and you could do your own hydrodynamics, right? And so on the top layer, the multi-body side of the fluid structure interaction is Chrono's multi-body dynamics engine. And this, as you probably already know, has like you have the smooth contact system and the non-smooth contact system, which is the CH system, smooth SMC and NSC. And you want to communicate between this bottom, which is the CFD part, the fluid part, and the top, which is the multi-body dynamics part. And you do this with this interface. Which does the communication. Like it understands what the multi-body dynamic systems need, and it understands what the fluid system needs and communicates between the two. So that's what's shown here. You don't really need to remember these class names or any of these details, but just an overview or a high-level idea of how this framework is structured. Okay, so a little bit more about the interface. I spoke about like the passing force and displacement. There is some more, you need to understand a bit more about what is the kind of data that we're exactly passing around. So for rigid solids, for example, from the multi-body dynamic side to the CFD side, we just need to pass the rigid body state. So that's the position, orientation, linear and angular velocity. And then from the CFD side, we just specify a rigid body wrench, which is the resultant force on the body, which is a fluid force and a torque, right? For a deformable body, it's a bit more complicated and you have to move around a lot more data, right? Because from the multi-body side to the CFD side, you need to pass each node state of the FEA mesh. That means for each FEA node, you need to pass its position and velocity. And similarly, from the fluid side to the MBD side, you need the force on each of these nodes. The communication, we now know what is communicated, but how it's communicated is handled through boundary condition enforcing markers. And I'll come to that in a bit, but all you need to know for now is there are two systems, the multi-body dynamic system, the fluid system. They communicate force and displacement, and these are the exact quantities that are communicated. Okay, so I'm going to talk about the numerical method a bit. So this is the smooth particle hydrodynamics, the SPH, which helps solve the partial differential equations for a fluid. Okay, so I'm going to go through a bit of math. The crowd is a bit split. Like there are some people who will think this is very basic, and some people who won't be able, who have not seen this before. But I think it's important to understand like a basic level of how this is done in Chrono, so that you can choose what parameters to use when you set up an SPH simulation. And people who work with SPH know that there are a lot of tricks and knobs that you can change to improve the stability and accuracy of your simulation. And you'll understand how to tune those knobs only if you know what they're doing. So I'll go through a bit of math So this is like the entire struct of all the SPH parameters that you can set as a user. And after this slight detour, you'll be able to understand what you are doing when you set each of these parameters. That's going to be the aim of this. So don't focus too much on like if you understand the math per se, it's okay to just get a high level idea of it. But I think it's important to understand how a parameter goes into the math, how it affects the entire simulation. Okay. So our model for fluids, right? So this is very general. This has nothing to do with SPH. It's just how over the years we have modeled fluids. So we have the continuity equation, which is the conservation of mass, and this big D over here is like the material derivative, not very important. But what it says is mass can neither be created nor destroyed. And from this, you can derive the incompressibility. So by incompressibility, what you mean is there should be no density change. And you plug that condition into this, and you get the divergence of velocity is zero. But basically, you have a fluid that is, and you know that fluids are not compressible. So you want to somehow encode this in the math, and this is how you do it. And then you have the Navier-Stokes equation, which kind of explains how like energy moves in a fluid, right? So you want to know, like in a fluid parcel, like how it accelerates, and you know that it accelerates when you have a gradient of pressure. It decelerates when you have a lot of viscosity. So that's the second term, like the viscous forces resist the motion, and then it accelerates because of body forces, which is like the gravity. So this equation basically tells like, oh, if I have a fluid, what are my external? This is like F equal to ma for fluids, basically. So this is the model of fluids. It's incompressible, and you need to know how it moves, right? And so that these partial differential equations explain that model. So in our implementation of this model of fluids, we make certain assumptions. We don't enforce incompressibility like in this formulation, which is called the weakly compressible SPH. You can enforce incompressibility with the implicit SPH. It is an option in Chrono as well, but I'm not going to talk about it today. What we'll for now we'll assume is you cannot enforce incompressibility, which means that your density is going to vary. So the change in density over time is not zero. You'll have some density variation. And to control that density variation, you have something called the equation of state, right? So this equation of state, this is the enum that you use to define it in Chrono. It's one of the parameters that I showed you in that big list. You can choose between different equations of state, and they have like different properties and different ways in which they control this density change. So if you're modeling something that's you want to model it like extremely incompressible, then you would choose parameters in the equation of state that make it that way. And you can choose between different equations of state. This is the default one. It's called the Tate's equation of state. So you have like an artificial speed of sound, and you basically increase this to enforce more compressibility. And this you can set as a user. So you can say my maximum velocity that I'm going to see in the simulation is 4 meters per second, for example, and the speed of sound should be greater than equal to 10 into. This comes from like the Mach number to make it less than 0.1. But and basically, if you set like a maximum velocity, we calculate an artificial speed of sound that provides certain incompressibility to the fluid domain. And these other parameters are also like the gamma is preset to 7. We don't allow the user to change that. And the reference density is just the density that you start with in the simulation. Okay, so incompressibility, that equation is now gone. You use this instead to control that incompressibility, right? So in the first slide over here, I showed these equations, right? But how would you go about solving this on a computer? Because analytically, it's not yet possible to solve these equations. You don't have an analytical solution from that differential, from the Navier-Stokes equation that says, oh, if my velocity is, if I have my if I know the differential equation, I cannot have a function of velocity that I can just plug into and get my velocity field. So you need to use a discretization to solve these equations. And that's the entire field of computational fluid dynamics, is to go from these PDEs to discretize it so that you get something that you can just solve and get like the velocity field. So what is SPH? SPH, coming back, like SPH is just it's a type of CFD where your continuous differential equations that are valid all over space, you discretize them. And the way you discretize them is you discretize them in a Lagrangian manner. So you have like points representing the continuum. These points carry mass and they move around, and you solve your equations on these points, right? So a fancy way of saying this is like it's a mesh free because you only have points. You don't have a computational mesh for the domain, and it's Lagrangian because the points carry the mass, and you solve all the equations on the points, right? So there are other ways to do CFD. You can do the finite volume method. You can use FEM to do CFD, but we choose this method for computational efficiency. It's easy to parallelize on the GPU, and it's like a growing field with a lot of ongoing research. And so it's one of the new ways to do CFD. Okay, I'm just going to pause here for 1 minute if you guys have any questions. Okay. So what do we need? So we have these differential equations. We want to solve these on a computer. You can notice here that I removed the incompressibility equation and I added this equation of state. The equation of state gives you this pressure that you basically plug into this Navier-Stokes equation. But yeah, so now we have these equations, and to solve these on a computer, I need SPH to give me how do I compute rho on each of these particles? How do I compute the gradient of V on each of these particles? And how do I compute the Laplacian of V on each of these particles? If I know these three things, I can basically solve these equations of motion because I have at each of my particles, I have these values. I can solve each of these equations on each of the particles. So the end goal of this section is to go from these partial differential equations into like a system of algebraic equations on each particle. And then I can just solve it on my computer, and I have like velocity at each particle, and so I know how my fluid is moving. Okay, this is a bit hairy, but you can ignore most things. But the main key thing to take out is you start with this. So here we're talking about how do I approximate a function. So I have a continuous function, but how do I approximate it at a particle? So you start from this direct delta identity, which says that if I want to find the value of a function at R, I place a direct delta at a point R dash, and a direct delta is like, it has like a peak only at R, and I integrate over the entire domain. And so I take, but the direct delta is like infinity at R and zero everywhere. So it's not possible to do this finite precision. So what we do is we make a kernel approximation. So it says that if I have a function that I want to evaluate at a point R, I'm going to take some R dashes, like I'm going to integrate over my entire domain, and I'm going to weigh all the functions at my neighboring particles, and that weight is determined by the kernel function W, right? So if you see here, R minus R dash, this gives me the distance from where I am currently to where I know my function R dash, and then I take that portion's weight, add it to my contribution. So integration is just a summation, and then I go to another R dash. I see how far it is from my current position. I take a weight from that and I add it to my function at that position, and I integrate and get my function at point I, right? So we are making a kernel approximation where we're going from a direct delta, which is like discontinuous and has like a huge peak at R but zero everywhere else, to a smooth function where um, like based on the distance from my current point to R dash, I can assign a weight. Like if it's too far, I don't want it to contribute a lot. If it's close enough, if it's close, I want it to contribute a lot. So that's what the kernel function does. And you can get like a smooth, something smooth that you can like do on a computer, right? There are some rules for the kernel function, and in Chrono we have 4 types of kernel functions. We haven't. There's a lot of research on which kernel function is best. I don't. Like the default is the cubic spline. The Wendland kernel is the one that is popularly used these days. But you can choose from any of these kernel functions. There are certain rules that these kernel functions need to follow, not important. But all of these kernel functions follow those rules, and you can choose one of these kernel functions. I would say sticking to the default is probably the best option if you don't have any specific preference. Okay, so now we were here. We have a way to evaluate a function at point R. given a kernel which assigns weights to neighboring particles, neighboring positions, right? But this is still an integral, and we convert in SPH this integral into a summation. So we go from this continuous integral to a summation, and this is what you would probably most recognize with SPH codes, is that if I want to evaluate a function at my point, SPH point I, right? I take the function at a neighbor j, I assign a weight to it based on my kernel function, and I add all of those contributions scaled by the volume of that particle, because you have like a volume integral over here. So if I have like an SPH, if I have like a cube and I assign and I discretize the domain with particles, and I want to find what is my function, like a density at particle I would look at all my neighbors that fit into this kernel, because the kernel goes to 0 after a certain point. I would look at all my neighbors that are within this kernel. I would compute the distance to those neighbors. From that distance, I'll get the kernel weight, right? That is my W. And then I would take the function value, the density at that neighboring point, multiplied by the weight, scale it by the volume, and add it to my contribution. So that this is how in SPH you go from this continuous function f to a discrete function on each of the particles, right? So there's like basically two things to remember. You have this kernel function that you decide, and you have to decide when that kernel, how that kernel function is, which is what like that based on the kernel function you choose, that is decided, and then how far this kernel function spreads. Like, do you want a lot of neighbors to contribute to your value, or do you want very few neighbors? And if you go back to your first approximation, that's the approximation we make, right? The direct delta function is very narrow. It's like just one is infinity at r. So the more wider you make your kernel, so the more particles you include in your kernel, the lesser accurate this approximation is going to be. And so the width of your kernel, which is called the kernel length, as you increase h, your kernel approximation is going to keep going down. But then if you look over here, going from the integral to the summation, as you all know that as you increase the number of points over which you do the summation, your integral is more accurate. So it's kind of like counterintuitive, because when I increase my kernel length and include more points, my kernel approximation error is higher. But then when I decrease h, I don't have enough points to integrate over, right? So SPH has this fight basically where you have like two length scales that you have to like jointly optimize for to get good function approximations at the particles. I'll come to that as well. The same way, you can follow like a similar style and get like the gradient of a function. You can derive like for each particle, I have this gradient of a function that I want to evaluate, and you can evaluate that using this formula. So some important observation is that to evaluate in SPH, to evaluate a gradient of a function, you don't need the gradient of the function at its neighboring points. So to evaluate the gradient of pressure at point I will not need the gradient of pressure at point J. And instantly you can see that this is good for parallelization, because I don't need to, I just need to, for evaluating the gradient, I just need to know the function value itself at my neighbor. I don't need the gradient. So this is like an explicit, like you can just like, once you know the function value, you can evaluate the gradient of that function instantly. So with the function gradient, there are like many ways you can write this. Like with the function value, you can write it only in one way, but with the function gradient and SPH, you can write this gradient operator in many different ways. This is one way. It's not a great way, because if you see, if I have a constant function f, right, your gradient of a constant function in continuous space, is 0. Like function is constant, you take a gradient of it, it's going to be 0. But then if you look at this formula, if plug in f equal to 2 for all space, for all j, you'll get a non-zero gradient, which means this discretization is not great. It has 0 order consistency. That means even a constant function will have the wrong gradient, right? So then you can modify this. You can say, you know what, like you can derive this. This is not just modified, but you can derive that. You can write the gradient operator also like this, where you take fj minus fi. And now you see that if you have a constant function f, right? So you plug 2 minus 2 will become 0, and your gradient will be 0. So at least now the constant function has the right gradient. So you can keep going. You have multiple ways of doing this. but the most accurate gradient operator, this is again part of SPH research, is when you use this kind of like gradient approximation, where you have this matrix L, which helps make this gradient operator such that even if you have a linear function, like if my density field is linear in space, if I discretize with SPH, I'll get exactly the same gradient that I would expect. So this L is called constant discretization. So this is an option in Chrono again. So you will have an option like use constant discretization. If you switch that to on, then you can expect your gradient operators to be more accurate at the cost of more computational effort. So evaluating this L is more expensive. You have to do this for each and every particle. So you switch this on, you get a more accurate simulation, but you lose out on time. So this is one of the options, as you can see. I use constant discretization. Same story for Laplacian. You can have like a constant discretization in that case as well. That gives the accurate Laplacian for a linear function. You can switch this to on. Over here, as you can see, there are two options: constant gradient discretization, which is for this gradient; constant Laplacian discretization, which is for this. You switch them to on. Again, you'll get more accurate gradient operators, but you'll lose out on computational speed. Okay, so putting it all together, I would recommend to start from the top. So we had these continuous partial differential equations. We found a way in SPH to like approximate a function, and this approximation, as I said, has like something you have to deal with, because you have to choose like the kernel length such that like you make sure that you have enough points but not too many points, because your one error will go up and the other will go up otherwise. So that's one choice that you have to make. But basically, if you have a continuous function f, how do I discretize it, right? And then you have a function, you have the same thing for a function gradient. This can be with discretization, so on the right, or without discretization on the left. But this basically tells you like, okay, I have a function, I know the value of a function at a point, but what if I have a gradient of a function? I know now how to evaluate the gradient of a function at a point. What if I have a Laplacian of a function? I now know how to evaluate the Laplacian of a function at a point. I can do this in many different ways. Okay, so you plug these in. So now f becomes like whatever field you want. In this equation, f will become rho, f will become v. And so you need like gradients, you need Laplacians, you need the actual function, like over here. You plug all of this in, you get these nice equations, right? So you went from continuous space partial differential equations to discretized algebraic, okay, not yet algebraic, I'll come to that, but discretized equations, where now I know if I want to find the rate change of density at a particular point, I know the density at my current point. I look at all my neighbors, J. I'll evaluate the kernel based on how far that neighbor is. Again, you have a choice there. And I'll evaluate their velocities based on where they are. I'll sum up all my neighbors' contributions, and I'll get my rate of change of density at my particular point. Similarly, if I want the rate of change of velocity, I would do this, and I would get the rate of change of velocity. And this pi I've replaced. This is the viscosity term, if you remember. And this is like a laminar implementation of viscosity, like the actual, like how you would if you just discretize the Laplacian. Okay, so that based on that, the viscosity can actually be artificial, and this is what is commonly also used in SPH, because the laminar viscosity is not very stable, as in like the viscosity for fluid is like very low, and so there's no good way to dissipate energy, and that makes the simulation unstable. So people usually use an artificial formulation of viscosity, which basically, again, big equations, but you have two options: artificial bilateral or artificial unilateral, in addition to laminar. So the laminar is the actual way of doing it. But if you want to improve stability, you do artificial unilateral or artificial bilateral, which I would say, so the only difference between these two equations is when there's an if condition here. So if you look at the artificial unilateral, Vij dot Rij, what does that mean? It means you have two particles I and j, it tells you whether they're approaching or whether they're going away. So in the artificial unilateral case, only when they're approaching each other only when they're leaving each other do you apply a viscous force and tell them to come back. Whereas in the bilateral case, you apply this artificial viscous force, irrespective of whether they're going away or moving together. So these are two options. The default is artificial unilateral because it's what's used mostly in literature, but you can shift to laminar or artificial bilateral. Okay. So that basically summarizes all the terms in this equation. So you now kind of know like what is happening at each particle, like what equations are being solved, and like what the parameter of what state does each particle hold, right? So as I said, the convergence of SPH is a bit funky. There are two length scales. One, and that's because there are two approximations that we make. One is that kernel approximation, where we go from a very narrow, thin, steep function, which is the direct delta, to a more smooth, broad function, which is the kernel. And since you don't have infinite compute, you need to cut that kernel off at some point. So that is defined by the smoothing length h, where you cut that kernel off, right? And then you also have like your continuous domain, and you're going to discretize this domain. You're going to add points at certain locations. Of course, the more points you have, that integration becomes more accurate. The less points you have, that integration becomes less accurate. And so that number of points is defined by particle spacing. So if I have a 1D line and it's like 1 meter, and I set my particle spacing as 0.1, then I would have 10 points starting from 0, 0.1, 0.2, 0.3. But if I decrease the particle spacing, I'll have more points, and that integration error will keep going down. Whereas for the smoothing length, it just defines how wide my kernel is. If I have a higher smoothing length, my direct delta assumption is going to become worse. But then when I integrate, like when I go from the integrate, I'll have more points. So it's a very complicated balance. I would say don't bother about this. So there's a popular work by one of the SPH, it's a work by Quinlan. I forgot to add a link, but this blog has a link to the paper. But what he suggests that if you're using first order constant discretization, so yes, it depends on that, and that's that matrix that we use, which reduces computational speed but increases accuracy. Then when you reduce h, like the smoothing length, by a factor of k, you must at least reduce the particle spacing by a factor of k 4/3. That's, I would say, as a user, just have an intuition about what is happening when you increase h and delta x, but use this as a way. So when you reduce your kernel, when you make the kernel tighter, you must also reduce the number of particles, because then only you will have enough particles in the kernel to do the integration accurately. So you can't just change the particle spacing and keep h the same. You need to change h and delta x together. Okay. Okay. So this is jumping a bit again. So I'm going to pause. This is pretty fast. So if you guys have any questions, or even if you want me to repeat something, that's fine as well. Okay. Okay. So you had these particles, and we had these equations where we know the acceleration, or in this case, the density rate change and the acceleration at each of the particles, but we want the density and the velocity at each of the particles, right? So you do this with time discretization, which is you use a numerical integrator. And I'm not going to go much into detail, but Chrono has a bunch of integrators that you can use. The Euler, Runge-Kutta 2, each of these have different accuracies. The Verlet, the symplectic integrator, which is good if you want to conserve energy, and implicit SPH, which we have not spoken about much. But you can choose any of these integrators. The default is RK2. It's pretty good. So if you don't have a particular, if you don't want to test anything out, leaving it at RK2 is good enough. But what this integration now does is, finally now you have a system of algebraic equations, and this system is not coupled. So for each equation, I can just solve them individually. So I can just go to the GPU, assign a thread to each of my particles, solve the equation for each of the particles, and I'm done. So SPH is very good for GPU parallelization. Okay, so that was all about SPH. So we went from the uh, partial differential equations all the way down to at each particle, how do I solve the partial differential equations? There were a bunch of parameters that came up that you will mostly have to set. And I think there is like some trade-offs between parameters, but you kind of have the idea of how you can tune accuracy if you want to and tune computational speed if you want to. Now we'll talk a bit about the interface between SPH and MBD. And as I said, the entity that does this is in Chrono, the boundary condition enforcing markers. This is done differently in other codes. So for example, in dual physics, you have something like a different way of enforcing these boundary conditions. But in Chrono, we enforce it this way. And what this means from a user's perspective is that you need to place these boundary condition enforcing markers on all your rigid and flexible bodies that you want to interact with the fluid domain. So what I mean by you'll need to place it is that if you have like a mesh, this could be like a circle, something simple, or like a complicated mesh, you need to place markers such that they are spaced the same amount as the SPH markers that are part of the fluid domain. And they have at least like you have at least like three layers of it. So you'll take like a mesh and you would cover the surface of the mesh with these markers, and you would ensure that the spacing of these markers is kind of similar to the spacing you used in the SPH simulation. And you would go like 3 layers deep, where the depth is again the same spacing. So and cover all the meshes in the simulation with these markers. So this is like a pre-processing step. You can't just use any triangular mesh. You'll have to take the triangular mesh and add BCE markers to it. Okay. I think I have it. Okay, but these BCE markers, I mean, you're not alone. Like Chrono provides functionalities to do this for you. So you input like a triangular mesh, and it would populate it with BCE markers. But from personal experience, that part of the code is pretty slow, and sometimes it does not produce markers that are like very accurately evenly spaced. So if you're very particular about this, Chrono also provides a way that you directly add the markers instead of the mesh. So you can exactly set the spacing and like the quality of the markers externally. But of course, if you don't really care much about it, you can just input the mesh and then Chrono will add BCE markers to it. Okay. So how these work is so the BCE markers are essentially fluid markers. They're just given a different name, but they have the state of a fluid marker in the sense that they have a velocity, pressure, and density. This velocity, pressure, and density is not obtained by solving any equations. That's the major difference from BCE markers and SPH markers. These are obtained by extrapolation. So we offer certain kind of boundary conditions which help give these markers this state of velocity, pressure, and density. So if you want the no slip boundary condition, which means if you have a marker and it's coming into contact with if you have a SPH particle and it's coming into contact with the rigid body, you want it to stick as much as it can. That's like no slip. Then you need to do this extrapolation of these quantities from the fluid domain in a certain way. That option, like how you do this extrapolation, is through two different methods. There are two different boundary condition methods that you can use. But in summary, all you need to worry about is that you have to place these BCE markers on rigid bodies. You have to choose a mechanism for extrapolation. Both the mechanisms are well established. There's not much you lose or gain by choosing one. But then the rest will be taken care of by Chrono. Yeah, so BCE markers, again, as I said, there are certain rules. You need at least 3 layers, and you need to make sure that they're same spacing as the fluid markers. Obviously, there is like a good conversion from mesh to BCE within Chrono, but we are continuing to work on this as one of the active developments, and we're also trying to like implement some sort of boundary conditions where you don't need BCE markers, you can directly use meshes. Okay, and there are certain ways in which you can, like the BC marker placement changes for flexible bodies compared to rigid bodies. There are more options, but for now I'm going to ignore this. The defaults are pretty good. But if you're curious, you can always go back to the slide, and this has all the details of how BC markers are placed on flexible bodies. Okay, so BC markers, all you need to know is you can't just use a mesh directly. You need BC markers. You can ask Chrono to do it, or you can do it yourself, and that will change the quality of the BC markers on the rigid body. And the extrapolation, the thing that makes all of this work, there are two options for that. You can choose either option. We have not noticed much difference between those, so I've not gone into much detail. Okay, there are other boundary aspects. For example, if you have this rectangular domain, you place like a wall, and wall again is like a rigid body, right? So you need BC markers for the wall to tell the fluid that there's a wall there. You place this wall, but you want fluid to like flow in this direction and have like an infinite domain, basically. Like, so if fluid leaves this portion, it should come out of the other one on the top. And so this is basically like a periodic boundary condition. And this option is also provided in Chrono, and you can set which axis you want this periodic boundary condition. So you only want it on X, you only want it on Y, you only want it on Z, you want it in all directions. And this will like kind of like help simulate like an infinite space. Like you could just have like a thin strip of fluid and then have periodic boundary conditions on each side, and the fluid leaving this side will come out from the other. So this is an option in Chrono as well. Okay, there are some more parameters. I know all of you are getting pretty tired by now, but there is things to improve stability. It's called XSPH. You have to set a particular parameter for that. There's another way to do this, particle penetration shifting. You have to set two parameters for that. And there's diffusion-based shifting, which is actually kind of like what is commonly used these days. And you need one more dimensionless parameter for that. These parameters, by stability, I just mean that, oh, you can get away with a smaller time step if you have these stability parameters, but obviously lower on accuracy, but at least the simulation will not explode. So as I said in the start, SPH, there are a ton of parameters. Each of them you have to carefully tune, kind of like for stability. And a good understanding of what you're modeling will help. Like if you're modeling something incompressible, you should tune the equation of state. If you're modeling something that's flowing, like if you want to like improve stability and you want to do it like you want to have the simulation fast, you can use these shifting methods to improve stability of the simulation. If you want modeling a very large domain, you need to space your particles. You can choose that, but there are like ton of options. And the thing about Chrono is we leave that to the user, because we want the users to know the code base and also like tune the parameters as much as they can. But we provide good defaults, so don't be scared for running a Chrono simulation FSI, because the defaults are good enough for any of the demo, for any like to start with. So the defaults will lead to a simulation that does not explode, and you can see something, and then you can tune it based on these slides and like what you understand of SPH. Okay, some more stuff, but I'm going to skip that and come back to this parameter list. So the integration scheme, we talked about that. There are many integration schemes. The default is RK2, which is good enough. The equation of state, which helps you tune the incompressibility. You can choose between the Tate's equation or the isothermal equation. The isothermal equation is the default. The viscosity method, which I said could be laminar, artificial unilateral, artificial bilateral. You can choose one of those. The boundary method, which is the way the extrapolation is done on the BCA markers. You can choose in that. You can choose options in that. The kernel type, which is like what kind of kernel, what shape of kernel you want. You can choose that. And the shifting method, which improves stability. So there are options for all of these, and you can tweak and tune and do whatever you want to test and like get a model up and running. Then there are these other parameters. From these, I would say the most important one is the initial spacing and the D0 multiplier. So the initial spacing is what I said, like you have space, you want to put particles. The number of particles you put will change the accuracy of the simulation. So the more particles, the better. And then the D0 multiplier, which I've not spoken about, is actually nothing but a multiplier that takes the initial spacing and gives you the kernel length. So as I said, H, the kernel length, and the initial spacing are not independent. You need to modify these together so that you get a stable simulation, because increasing one and keeping the other the same is going to lead to like inaccuracies in your simulation. So by providing D0 multiplier, we force you to change them together. So if you change the initial spacing and you set the same D0 multiplier, the H is going to automatically change, right? And that's what defines the errors, right? So our default is 1.2, which is actually on the lower end, like as in this is the fastest you can get away with, like the smallest D0 that you can get away with. As you increase D0, your simulation speed is going to go down, but your accuracy is going to probably improve with the same initial spacing. Okay, and then the max velocity, this goes into the equation state and has helped to tune the incompressibility. Then there are a bunch of parameters for shifting. I didn't go through them in detail, but you can just leave them as defaults. These are based on the shifting method you use first, and each shifting method has its own parameters. So you can vary those parameters if you want, but they're very good as defaults. Like you don't need to touch them. Then there's the when you use artificial viscosity, you need to set a parameter, leave that as default. It's fine. There are some other ways you can improve stability. I left that out of these slides because it's just too much. But yeah, so if you want to go about generating an SPH simulation, I would say pick the defaults, let them pick the parameters such that they're defaults, run a simulation, you'll see results of it, and then kind of like try to narrow down as to what parameter you want to tweak based on your application, and maybe look at these slides and see what each of these parameters mean, and like kind of understand if I increase this, what will happen, if I decrease that, what will happen, and choose a set of parameters that will lead to a stable and as accurate as you want simulation. Okay, so now to the code. So I'll also be talking about the CRM, which is the same theory. So I won't be repeating the theory. So now mostly it'll be coding. So first we'll go through like that example that I showed you of how to set that up, and then we'll take a break, and then I'll talk about the terrain model and how to set the terrain model up. Okay, so just a precursor, like I didn't know what Chrono was before I started my PhD, and I still don't know 90% of what Chrono is, because Chrono is huge. It has a lot of ways of doing the same thing, which is very different from other tools because they just give you one way of doing something. So you lose some sort of power, but then you're comfortable because you don't have to choose many things. Chrono is the opposite. You have like 100 ways of doing a thing. You can choose whatever you want. All the parameters you can change, do whatever you want, break things, which also makes Chrono hard to use because you have a lot of decisions to make. So what I usually personally do is I just look at the demos. There are a lot of demos. It's taken a lot of work to like compile this list of demos, but I always start from that. So the workflow that I usually pick for even the demo that I made for this tutorial is you look at an existing demo to understand the structure. Like what do I need to initialize, when, and how? That's what you want to gauge from an existing demo. Copy paste as much as you can. Do not remember the structure is my advice. I mean, obviously, as you make more and more demos, you'll eventually remember it, but you do not need to remember it. So copy paste as much as you can, and then massage and start modifying it. See and go to something that will work for you. Something that has worked very well in the recent past for me is using AI code editors. It works very well with Chrono because once you open the Chrono folder with these editors, it indexes the entire code base. Since Chrono is open source, we don't care if they index it and use it and do whatever they want with it. So you open these editors, you open the Chrono folder in these editors, and you just chat with the editor, and it will make a Chrono demo for you. I'm not kidding. So tell it like, look at this demo. I want a vehicle. Look at these demos that describe how to make a vehicle. I want a fluid domain. Look at this demo of how to make a fluid domain. Combine this and give me something. Attempt one is going to be bad. That'd be bugs, but it is what really speeds up the initial process, which is what most people get scared of, like the initial setup. Because after like an initial demo setup, like tweaking and tuning is much easier. Yeah. So let's write some code. Before that, I would like you to clone the Chrono tutorials repository. If you don't have it cloned, it's fine. The Dan's zipped folder has the tutorial. So if you have that, it's fine. But the most latest, I edited a bit after Dan sent it across. But if you can, you should clone this Chrono tutorials repository. And I would also just clone Chrono as well, because I mean, you don't need it to run anything, but I will go to the Chrono code base. I'll go through a demo. I'll tell you what I understand from it and how I translate it into a tutorial which we're using today. Before that, before we even go through the demo, I just want to add this slide, which is like a summary of like what I spoke about. This is like the entire workflow of setting up a fluid structure interaction problem in Chrono. And this is all you need to remember. Instantiate the multi-body system dynamics, the multi-body system. Parallelly, you need to instantiate the SPH system because you have two systems now. One is the multi-body dynamics and one is the smooth part hydrodynamics, which does the fluid simulation. Each of these has its own parameters, which is why this goes out to the right. For the SPH system, you need to set the SPH parameters, which defines like where you place the particles, what is the kernel, what integration scheme, what equation of state, all of that. And you need to define a SPH computational domain, which means that in this box, I'm having an SPH simulation. I'll show you how you do that in the code. But these are the two things you need for the SPH side, or the fluid side of the simulation. Similarly, on the multi-body side, this is pretty standard by now. You need multi-body, you need bodies, you need joints, you define those joints, you add visual shapes to them if you want to visualize, you add collision shapes to them if you want the bodies to collide, but you instantiate that separately. So you do these two parallel things. You combine them into a fluid structure interaction system. So the fluid structure interaction system knows about the MBA system and the SPH system and can communicate and can help the user communicate between them, right? So you do all this initialization of both these systems. You tell the FSI system, this is my SPH system and this is my MBA system. And now you have an FSI system, right? So one additional thing that you need to do for SPH is, it goes back to those BC marker things. You need to say to the FSI system, like, don't look at all the bodies from the MBA system. I don't care about all of them. I'm going to give you a set of bodies from the MBA system, place BCE markers on them, and let the fluid system know that these bodies exist. So that is what I mean by this orange block. So add MBA's bodies to FSI system as FSI bodies. So what this enables is, like if I have a tire and I want the tire to interact with the fluid, I will add the tire alone, not the entire vehicle because not required. I'll add the tire alone as an FSI body. I would communicate that information to the FSI system. And what the FSI system will do is it'll take the tire, look at its geometry, add BCE markers, and make it ready to interact with the fluid. So once this is done, you initialize the FSI system and you run your simulation. So this is all you need to remember. You need to remember that you need to set the parameters for the SPH system. You need to set the MBA system. You need to couple them through the FSI system. You need to tell the SPH system what bodies it needs to care about. You do this through the FSI system, and then you just initialize the FSI system and you can do simulations with it. Okay. So now I'm going to go to the code. Okay. So this is not the final code. So this is why I asked also to clone Chrono, and this is a cursor window. You can see chat here. But what I've done is I've gone to, this is the entire Chrono source code. So I've gone to demos. Thank you. Okay. Oh. Oh. Give me a couple of minutes. Okay. Great. Okay, so this is what I've done. I've gone to, this is the Chrono repository. I've gone to source. And my goal here now is to look at
Huzaifa, share the
demos
screen.
and see what I understand from it. So I've gone to source
Huzaifa,
and I've gone to
can you share the
demos.
screen?
And I want, first I want to have a vehicle, right? I want a vehicle moving on this floating block with fluid. So I want to first understand how to like have a vehicle simulation. So I go to vehicle demos, of course, and I know that any of the vehicle demos will work. So I just go to one which the CRM terrain, because the CRM terrain already uses FSI, so that demo will be most helpful to me. Just reading the code, you can see that how a vehicle setup is pretty straightforward, right? This is in C++,
Huzaifa.
but the same thing carries over to Python. It's basically the same API. So as I said, look, I have a CH FSI system. And in this case, because we're using a CRM terrain, we have a special class called CRM terrain, but that basically requires a MBS system, which I define all the way up here, right? So for the vehicle, it's easier to like create this vehicle and then take the system from the vehicle. This is just a utility that is easier. Like instead of having a multi-body system and then adding all the vehicle stuff, you can just create a vehicle based on some arguments and get the MBS system from it. But the terrain specifies the terrain, as you can see here, take the spacing. And so like from this, you get an FSI system. So I need these two kind of systems, and I have this FSI system. And then you can see over here that you just like assign all these material properties for this FSI system. So here I'm just going very quickly because this is not the actual demo. And so I'm just trying to show you the structure of another demo so that you can translate it. So I just define the material properties in this case of the terrain, the SPH parameter, the integration scheme, initial spacing, D naught, all of that.
Huzaifa, can you hear
And
me?
so now I have the two systems, and I have those two systems
Huzaifa.
coupled into this fluid structure interaction system, which helps communicate. And then now I have to add the bodies from the MBD system that I want in my fluid system. And this is what in this demo, this is the function that does it. So as you can see here, it takes the terrain in this case and adds an FEA mesh to it. This is because the tire could be like a mesh or a rigid body. If the tire is a rigid body, it just adds a rigid body to it. So that structure is basically the same across all the demos. And this is from like a random demo in Chrono. So now going to the actual demo that we are working with. Mm-hmm. I hope it doesn't go away. Okay, great. So this demo is, if you're in the GitHub repository, it's under the Magic 2025 folder and FSI. So in FSI, there's tutorial vehicle FSI floating block. So that's what I'm going to talk about. If you have the zipped folder from Dan, it's the same folder structure. So you'll find it there as well. Okay. So we go to the function main, and over here you'll see just some basic simulation parameters that you would do for any simulation. It does not relate anything to SPH. So you need to set like an end time, how long the simulation is, and these are some parameters that define whether you want output from the simulation, whether you want to do rendering, at what frames per second you want to do rendering, and stuff like that. And then now something more specific to SPH, which is you need to define your dimensions of your fluid domain. So we want that pool, and we say, okay, the pool is going to be 4 meters cross 2 meters cross 1 meter. And like the pool, the fluid in the pool is going to be that big, but the pool itself is going to be a little bit bigger in the z direction. So that's all we said. And then these are just helpful. Like I'm not setting my SPH parameters. I just have a variable that says my initial spacing. So my 4-meter pool, I want particles every 0.1 meters, right? And this is common across all 3 directions because the initial spacing has to be the same. You can't use different initial spacing across the dimensions, right? And then you want the step size of the simulation. Since the simulation happens like in a co-simulation setting, you can use different step sizes for your multi-body dynamics versus your fluid domain. So if you find that the fluid domain is, you can use a step size of 1e minus 3, whereas for the multi-body you need a 1e minus 4 time step. You can do that without any problems. In this demo, we use a single time step for both the multi-body system as well as the fluid system, and that's 1e minus 4. So as I said, so first you define your MBS system, and we use a smooth contact. So Chrono CH systems. This defines the multi-body system. And similarly, I have an SPH system, right? This is the same class name that I showed earlier. So CHFSI fluid system SPH. You combine these two systems and you get your FSI system. So this takes the MBS system and the SPH system and gives you an FSI system. These are some parameters. This is not very important. You can comment it out if you want, but I'll keep it there. And you can set the gravity, of course, for both the MBS and the FSI system. Okay. Then you can set the step size. So this is now coming into the parameters of the systems. So you need the gravity acceleration for each of the systems. The default is anyways Earth gravity, but if you want to change that, you can. And you need to set the step sizes of the two systems. As I said, we're using the same step size over here. Additionally, now I have my FSI system, and now I can go ahead and define properties, the SPH parameter properties, as well as the fluid material properties. So here, there's this struct called fluid properties. I set a density and a laminar viscosity. Note that if I change to an artificial viscosity, which I will in a later part of the code, this is null and void. It doesn't really matter what you set here. But I'm just showing that if you want to use laminar viscosity, you need to set it here. So these are my only two fluid properties that I really want to set. So I set them and say set CFD SPH to my system, which is the SPH system, and my fluid property is set. Now I need to set my SPH parameters, which are all those things that I talked about: the integration scheme, the initial spacing, the D0 multiplier, the max velocity, the shifting, the artificial viscosity. So once I set this, it means I'm using artificial viscosity. So again, this is now useless. So I can set the artificial viscosity, the boundary condition method, the viscosity method, some other stuff. But this, if you look at any other demo, like if I go back to some other demo, so this is from the old demo that I was talking about, is the same. Like the way you set it is the same. So you can just go to a demo, copy paste the settings for that, and then tweak them. You don't need to remember that, oh, I need this struct or I need that struct. Use the demos as much as you can and set these parameters based on what kind of simulation, what you're trying to simulate, right? And so then you just call set SPH parameters. And so now your SPH parameters are set, your fluid properties are set, right? And so this is what I was talking about for the computational domain. So why we need this is that when I set a computational domain around my fluid, right, any SPH particle that leaves that domain is frozen instantly. So they become like ghost particles pretty much. And this helps like limit simulation of particles that are very far from where we care about, or the domain that we care about. So you can set this computational domain to be very tight with the where your SPH particles are very loose based on what you want to simulate. But the computational domain is a box, so it expects an AABB, axis-aligned bounding box. For defining an axis-aligned bounding box, you just need 2 points, the left bottom corner and the top right corner. You define those 2 points, and then there's another argument. So let me just. Okay, so then you define another argument that says if I have which asks whether there's a periodic boundary condition. So if I have a computational domain and I set my y as my periodic boundary condition, which I'm doing over here, particles that leave the computational domain in the y direction will come out through the other side. Okay, so this is like I'm simulating pretty much like an infinite domain in the y direction, and my x and z is fixed. And if you go back to the video, okay, I'm not going to go back. We have to open YouTube. But if you run the demo and you see the video, you'll see that the pool, facing the pool, you don't have, like, you have particles that could be leaving and coming out from the other side of the pool. Okay. So you set this computational domain, and now once you set the computational domain, you're allowed to populate this computational domain with SPH particles, right? And you want to populate this SPH domain this computational domain with like particles with this spacing. So you define a box. It could be however big, but within the computational domain, and you define its dimension, and you use Chrono's grid sampler because you want the particles to be spaced evenly. So a grid makes sense. Use the grid sampler to sample these points. So now, given the box and the box's size and the spacing between each particles, I have like a box full of particles, right? And then I go and I add all of these particles to my SPH system. So I loop over all these particles, so my points that my sampler has given me. I add these points, I specify initial conditions. So over here I specify an initial pressure based on like the depth of the pool. So as you know, like as you go down, the particles will have more pressure. I define an initial density and say that, okay, this particle is over here, it has this pressure and this density. And my SPH system now has a computational domain, and within that computational domain, it has particles. Okay, so for now, the SPH system is doing well. Like it has particles, it has a computational domain, all of that is set. We'll go back a bit to the MBS system. So in our simulation, we have like this pool, and we have like a platform on the left and the platform on the right, and we want to like make these objects. So the next portion of the code is just creating these objects. So we define a material, like some sort of material with Young's modulus friction, whatever. You can use defaults for this as well. And we define this ground. And to this ground, we add the bottom wall, which is the bottom of the pool. We add the left wall, which is the left wall of the pool, and we add the right wall, right? And then we add the left platform, which is where the vehicle drops, and the right platform, which is where the vehicle stops. And this code, you could take from any like MBS demo. Like I genuinely, like if you remove this code and ask me to type it out, I wouldn't be able to. So just copy paste from some demo, and you can see that it requires like how big the box has to be, where the box is, what shape do I want to visualize the box. So I need to use a visual shape box. Whether I want to add textures to make it look good. As you can see, I added like a concrete texture. Then to the ground, which is my CH body, I have this box with this visual shape. I have this box with this collision shape, and that's about it. And so I construct this ground with all these visual shapes, these collision shapes, whatever box's size I want, all of that. And I add that ground, that CH body, which has all this information to my MBS system, right? But remember that now this MBS system, like I want the pool portion, like the pool walls, to interact with the fluid system. So I need to generate BCE markers for the walls of the pool. And this is what this code is doing. So there's a utility function that if you have a box container, you can very easily generate BCE markers for that. So I call that function. One interesting part is this is a bit confusing usually for users, this argument. So create points box container. This, as you can probably guess, is the dimension of the box, which is the same as the dimension of the pool, because that is what we want to add. And this over here is in what direction do I want to add BCE markers, right? So I want to add along positive x and negative x. So I have two here. I want to add no BCE markers along y because I have periodic boundary conditions there. So I don't need BCE markers. And I want to add BCE markers at the bottom of the pool, which is minus z. So if I wanted to add BCE markers along y, I would set this to 2. And I would have BCE markers along plus y and negative y. But the periodic boundary condition would not make sense then. If I wanted to add BCE markers only along negative y, I would do minus 1. If I wanted to add BCE markers only along positive y, I would do plus 1. But over here we have 0. And then similarly for z and all of that. So with this single integer vector, you can define in which direction you want to add these BCE markers for this particular box. Okay, so you've generated these BCE markers and you just add FSI body. So you let the FSI system know that there is this box, it has these BCE markers, please add it to my system and let the SPH system know. Okay, so this was the container of the pool. Additionally, you would also need to, you also have this floating block, right? So we generate this floating block, we give it a size, we give it a density, we give it volume, mass, inertia. We say where it is, and we define a chrono body, give it all of these properties. We set its pause. We say it's not fixed, so do dynamics for it. We set its mass, we set its inertia. We say that it has to do collision because the vehicle has to move over it. And we give it like a nice visual shape. We give it a texture. We give it a texture. We add the visual shape and the collision shape. So this is all like MBS stuff, not related to fluid, but making this box look good and making it have the right material properties. We add that box to our MBS system, but again, we need this box to also be in our FSI system. So we do the same thing. We create BCE markers with the same function. And notice that we don't have any argument here. That means it will just create everywhere BCE markers. And we add that body with the BCE markers to the FSI system and say, we need the SPH system to know that this body exists and it has to interact with the fluid. Okay, then we create the vehicle. This is like one of the other functions that I'm not going to go into this, but this is like how you would set up a chrono vehicle. You can use like JSON files to define like engine parameters, transmission parameters, tire parameters, whatnot. So this is all MBS where, yeah, so this is all MBS, right? Where FSI comes in is, again, we want to let the FSI system know that, hey, look, the tires might interact with the fluid. So add BCE markers to them and let the SPH system know. And that's what we do over here. We say we get the tire from the wheel, we add an FSI body, and we give it like the wheel spindle, which is actually the only which defines the CH body for the tire. We give it its geometry, and we add that to the FSI system. So now, according to the MBS system, there is like a vehicle with suspension, engine, blah. There's these platforms, there's this wall for the pool, there's this floating block. But according to the SPH system, I just have a computation domain. I have my SPH particles at these points, and I have and the SPH knows that there's this floating block that might interact with me, and there's these tires that might interact with me. So with this, I have my two systems ready, right? And then I can basically just create, initialize my system. So this is like done. Now my systems are ready for simulation. After this, all of this code is just where do I save my output, which folder? You can have runtime visualization with VSG, and there's just settings for that, like what is my window size, what is my background color, where do I set the camera, all of that stuff. But all of this, if you just use some other demo as basis to write all this code. Okay. And then I define some sort of like logic for the car. Like I say, okay, wait for 0.4 seconds. For 0.4 seconds, don't do anything, just apply brakes. Then after that, apply a throttle. That scales with the time. So more and more throttle as you go more and more in time. And then once I reach the maximum distance that I want you to reach, brake. So this is like a basic control, but this controls the vehicle and synchronizes the vehicle's motion with the fluid system. Um, yeah, and this entire loop is doing the simulation. So this top part was just the controls that I just described. You have some rendering stuff over here, but you synchronize the vehicle based on the controls, and you use your system. So FSI system, which is important here, which has the MBS system and the SPH system, and you just say do dynamics for DT. And it'll do dynamics, how many more steps it takes, how many steps it requires based on the time step till DT has passed, and then you can come back. So after every DT, I can do something like print, SPH, get density, for example. I can print the density for if I care. But this is the simulation loop, and you can just like propagate the simulation and stop it whenever you want, print whatever you want, output whatever you want. Um, um, and like run the simulation. So I'm just gonna like pause here if you have any questions with like the entire structure, or if I made a mistake or something like that. Anything? Yep. So between each rigid body, the contact is handled by the multi-body system. So it's smooth contact, which is what we said. So not related to fluid. Yep. I know. Um, yes. Yeah. So the question was that so in SPH simulation, you have the CFL condition, which like if you have a spacing between the particles, you want your information to be captured without skipping like a grid. So you cannot just set your time step. You need to set like a small enough time step such that all your information or your pressure waves are captured. So the answer is right now in this one that I'm showing in the tutorial, there's a fixed time step. But in the Chrono source code, in the development branch, we have a variable time step based on the CFL condition as well as like the maximum acceleration. So very similar to dual physics, basically the same implementation, which kind of like automatically sets your time step. So it's a variable time step scheme, but that's not in main yet, like the main code. It will be added in the upcoming release. Yes, exactly. Yes. So follow-up question is that now if I have like a CFL condition that takes 1e minus 5, but I have my multi-body system that takes 1e minus 4 time steps. So I have to do 10 time steps for the SPH simulation before I have information from the multi-body system. So right now we just do that. So if there's a difference in time step, we propagate the SPH system, how many hour time steps it takes to like match the MBS, and only at that portion we exchange information. So for 10 time steps, the SPH system is using the position of the multi-body, like the bodies of some old time, basically. If that does that answer your question? Yeah, yeah. So that's one thing. So if you use a much smaller time step for the SPH system, um, even though it's taking more time steps, it's using the information from the multi-body dynamic system at some old time because that's just not stepping at the same discretized time step as the SPH system. So that's a detail that um, is important in many situations where your bodies are moving very quickly and you want to like really capture that. But usually in like this case, it's okay. And plus we set the same time step, so you don't have that problem right now. Okay, so any other questions? Ah, yes. So actually, we provide an option to use both. Yeah, we can discuss that. Okay. Okay, so I take it that there are no more questions, and I'm just going to run the code now. So I'm going to connect. I don't have a GPU locally, so I'm going to connect to my workstation in the lab. Okay, so I have a terminal window open. I don't know how clear it is. Okay. Okay, never mind. Okay, so if you look at the path here, I don't know how visible it is, but it's basically I'm in the FSI folder from the GitHub repository. I'm just going to see what is there in this folder, and you can see that this is the tutorial that I want to run. Let's hope it runs. Yeah, so this is what the video showed as well. So you'll see a lot of windows like on top of each other. That's like a VSG issue, but you can just move them apart. There's a lot of information here if you're curious. I think it's better if you see it on your screen. I can't see anything here. But the fluid moves, the field that you're seeing in the visualization is the velocity field. You can see a lot of particles like flying and like going out of the box. So you might want to like set the computational domain tighter so that when they leave that pool, they're frozen and they don't like fall and go all the way down or whatever. I'm just going to run it again. The other, yeah, yeah, I think, and you can see that. Let me. So here you can see the BCE marker, so you can enable that in the runtime visualization. And you can see that the pool has like on X and Z, but nothing on Y because as we said, Y is periodic. So you can have fluid like leaving that pool from one side and coming back on the other. So that's about it for the FSI one. For editing, like for the CRM demonstration, like you'll be editing some code. But for the FSI one, I wanted to focus on the SPH theory and like the options available. So that's about it for this tutorial. If you have any questions, you can ask them now, or I'll stop sharing and pause the recording and I'll be in the room. And the next one will start at 2, so you can take a break, do whatever. But yeah, let me just leave it at this slide. Okay, so yeah, any other questions with respect to the code or like the SPH stuff? So is Holmes, which is like from a paper whose first author was Holmes, so we just named it Holmes. But it mainly, yeah, it actually is the same for CFD, like there's no change. But in CRM, when you're solving the stress equation, it extrapolates the stress a bit differently. Yeah, so if you're just using this code base for fluid dynamics, you can use Holmes, but it won't affect your simulation at all because it's the same as Adami for the variables you care about. Yeah, these are related to the two boundary condition options that we own. I don't think I've. So I think with respect to, so I have only ran a lot of CRM simulations, and in that case, the stress, the pressure that comes out of the stress is enough to prevent this interpenetration. But CFD, I would not be the right person to ask, I guess. I think Luning, she uses a lot. She uses FSI a lot more for CFD than me, so you should talk to her probably for this. Yeah, for running. Yeah. Yeah. Okay, so I'm gonna pause for 30 minutes. I'm gonna be around, but we'll start the other tutorial at 2. Yeah. So see you guys.
Thanks for coupling. So internal, so
Okay, nice to meet you. Was that fun?
Josh. We have an internal DEM code, Rocks 3D, and it does the classic. You give me kinematic information, I'll give you forces, right?
Mhm.
And it works until it doesn't work.
Okay, so what is the major problem that you?
It depends on the, for instance, you have very flexible bodies in there,
Mm.
then you need to communicate faster.
Mhm.
Or the other one is the other solver that we have, it's all in the house built code. The other solver is a differential algebraic equation
Mhm.
solver. So it's just a whole bunch of some ODE, some algebraic equations, some whatever. And it really likes to know partial derivatives.
Oh.
It likes to know, like, those are your forces. I get that, but how would your forces change if I were to change this thing? Because that way it's a better understanding of the system as it does the integrations. So and again, the issue is it works until it doesn't work. Meaning, I'd say the majority of all simulations we do, it works for it. There's so often you get one where it doesn't work.
Mm. Yeah, I think that is like there are many different ways you could do that, right? You could like force. You can do like something like an implicit setting where you solve both systems together, and that's the constraint.
The DAE system is implicit, so that can do it just fine.
Yeah, but
But our soil simulator, I mean, you have so much state, right?
yeah, so you just do everything
tens of
explicit.
millions of state variables, and it just like, it can't do it.
Yeah, yeah, I agree. Like that is like something that has not been solved for.
Okay, so you haven't seen any big solution for either.
No. So
Okay.
the best thing you could, yeah. So the best thing you can do is couple the system, which is like the portion one that I talk about, monolithic. So in that case, you are enforcing incompressibility and non-penetration at the same time. So you're solving one big system.
Yeah, so we COSIM because they're completely different code base.
Yeah. So COSIM,
Yeah.
this time stepping is like very tricky. Like you have to make sure that you're simulating, which is very much harder at DEM because you're simulating that at like 1E6 minus 6 and rigid body probably at 1E minus 3 or something like that.
Oddly enough, we have some simulations where our rigid body simulator, which also includes hydraulics, is at 1E minus 8. It's
Oh.
lower than the DEM. Because hydraulics, we
Higher
balance
frequencies, yeah.
shockwaves within the system, and we have to pick up all that stuff. So yeah, we will sometimes actually have them have a flip on us, so that the DEM is actually the faster one.
Wow.
There was a talk, so I've been covering the magic stuff for about 10 years-ish,
Mhm.
when Dan first started it. And there was a guy, but his paper was in German. So I downloaded the paper and I've never read it yet.
Mhm.
It just occurred to me about last week, like I have to send it over through some AI system to translate for me.
Mhm.
But he was at the magic thing about 10 years ago, and he gave a talk on coupling those things. I just don't remember how it worked. I don't know if you guys looked into it at all. Because he looked at it in terms of like, across that coupling, there's some time frame across which it works, or like you gave me forces, then I assumed your forces were constant, or maybe I did some
Or extrapolation,
or
yeah.
something. But there's an energy that's being created and removed across that time frame. It's an extra math that you put in there to couple it together.
Mhm.
And so, because when you talk about it, like, this is what we do, there's other ways, and we're just going to talk about that.
Yep.
I was curious if you had looked into this.
So with SPH, we don't have this problem a lot because the SPH explicit time stepping and this time scales between the MBA system, which you usually use smooth contact. So time scales are very similar. So the basic plain vanilla co-simulation setup works perfectly out of the box. We haven't like faced major issues with that. Because there's also this other layer of communication between the MBA system and the fluid system, which is through those markers. And those markers are in the FSI system and they accumulate force. So we don't like accumulate force per time step and then add each time step. We just simulate the system, see how much force is accumulated on the BC marker, and then pass that as like a wrench. So that approach,
Because you accumulate the force going to each individual one, but you accumulate over all of that.
yeah. So you have
to-
exactly. So you have the accumulation over all BC markers, and that accumulation is kind of like just fluid dynamics basically. So that way there is this, I would say, smoother way in which we pass the force, because not just contact forces, it's like averaged out with the kernel and stuff like that.
So that's usually why our simulations work, is when we have an implement digging in the soil, you're not touching one part of it, you're touching many. parts.
Exactly.
So it just kind of blurs out.
Blurs out.
That's what I'm saying, but we had one particular bug, which I dealt with once.
Mhm.
And it's because when the machine first touched the pile of dirt,
Mm.
you always touch one part of it first.
Oh yeah.
And what would happen is it's all penetration based, it's not DVI. So the
Mhm.
force would start to ramp.
Go crazy.
And then that huge force is pushing on the machine,
Oh, man.
so integrated weird, to then cause it to move to a weird spot. And then the DM goes, oh, you're going over there, then here's your force.
Yeah.
Vibrate like crazy
Mm.
until it penetrated in the pile.
Mm.
And sometimes it vibrates so bad that it would flip the machine over. Like,
Whoa.
this is a,
Okay.
however many 100-ton machine. It's
Mhm.
not even flipped over by parts. So it's like that communication layer has been a curiosity to us. Because when it works, which most of the time it's fine, but the cases we find where it just doesn't.
Yeah.
Those of us who write the code are always concerned, like, can we detect that
Mhm.
it went wrong? We don't even see a way to do that.
Yeah. Yeah. That's very hard. That's very, very hard. I would say the person in our lab who has worked with this stuff the most is Radu. I don't know if you know him,
Yeah.
but he,
Is he still in America?
no, he's in Switzerland, but
Okay.
you can email, he's always working. So you can email him and he'll be very, very happy to talk about this stuff,
I'm actually
because
here.
I think he did publish some papers on this as well, like this coupling. So I think from that perspective,
Yeah,
the German,
We've talked to Radu several times.
okay, yeah, but I think to be honest, there are only a few ways you can do this, right? You can extrapolate, or you can find some theory that helps you define exactly when you need to communicate and how much, which is what that energy thing probably does.
Yeah, and that's what we just have not seen a good solution for.
Yeah.
And when I go to look for solutions for this, last I looked like 3 years ago, I see no papers.
Yeah, I don't think
Only that one guy ever talked about it. I can't read his papers. It's in different language. So
yeah,
my trouble's like, I think as a world, we're missing out on something here. There's something, I think we have survived with ignorance about that interface. We've said, well, it's close enough. Like it
Yeah.
seems to work well enough.
I agree.
But I don't think we can mathematically quantify the amount of error being introduced into any simulation.
Mhm.
Because we look and say, visually it looks reasonable, or it's not reasonable, it must work.
Mhm.
I don't think we've ever quantified it.
I think, I think it's a big problem. Just you talking, one solution could be, so something that I've seen in robotic simulation is something called continuous collision detection.
Okay.
But what they do is they have some history of the body, right? And they extrapolate the position of the body to find out the time step they need to take to capture a collision. Right. And how that works is you have like a complete space of what how the body is going to work. So you check each space.
Configuration space.
Configuration
Yeah.
space, right? So I think something similar might work with this.
I mean, in robotics, if I've got 10
Exactly.
linkages.
It doesn't matter too
Be-
much
yeah.
in robotics.
I've got 10 million.
Exactly. So DM makes it. I think DM is probably the one field where this matters the most, right? Because you have huge, very different mass scales, and
So another field is will COSIM through FMI, FMU,
Mm.
functional mockup interface.
Mhm.
And that could be for some other thing, like it could be the engine or it could be a powertrain, or it could be, I don't know what. We don't know what timescale it's on. So again, when you try to couple, anytime you couple and COSIM, you're always left with how accurate. It's like we just assume that the other guy's not changing across my timestamp. Well, my timestamp's small, right?
Mm.
You need -4. It shouldn't really affect, but it does matter.
Yes.
And that's what I'm saying. I've thought about this for years, and I just feel like as a scientific community, we're a bit ignorant to this.
I agree.
We just ignorant. Just turn a blind eye and say, I don't even want to look over there because I'm not seeing it. So yeah, I'm just
Interesting
curious
problem.
because we started talking about like, oh, maybe they have started looking into all.
None of us, because it's never been like but it's never been like something that we have focused on because we have not faced the problem, I'd
Exactly.
say.
Exactly.
And I think this helps. So now,
Your comment on that, the FSI, the BCE markers, you have so many of them.
yeah, it averages out.
Yeah,
If you,
that's plausible.
yeah, and I've seen like, if you just look at the force on one BCE marker, it'll be crazy.
Yeah.
But then what helps is we smooth out that and then apply like a total wrench on the body.
Yep.
So that smoothed out force is fine.
Yep. Yep.
So I think it's much more less important in this setting.
Okay.
But I'm pretty sure it's sad that it's not a field of research. Not much progress.
Interesting.
Not
That's
interesting.
the problem. That's sadly how research goes. Since have a
Yeah,
sellable topic.
exactly.
Hard to get one.
This is something like that is not, you won't get cool movies out of it.
Yeah.
The movie will be the same.
Yeah, exactly. And the real question is like, how different are the results?
Exactly.
We're only talking about a 1% change in, except for those couple cases where it is highly noticeable. But if most of our simulations are hitting that, then we don't worry. So I think it's just like people haven't worried too much about it. But
Yeah.
it's hit it every so often.
Yeah. Interesting problem.
Right. Thanks.
Yep. Thank you so much. Thank you. Hi. I'm Jose. Nice to meet you.
Nice to meet you. Thank you so much for speaking. Very, very awesome. That's very helpful.
Thank you.
Out of curiosity, so uses Lagrangian particle method, right? And I was curious on if SPH is capable of doing something like segregation for like a simulation. I know those. I've seen some things that uses Euler Lagrangian,
Sublimation as in
like solid to gas,
solid to gas. Oh. So
like a total phase change. Like you're able to somehow model the discretize to gas, since like you don't, if you don't account for the atmosphere, like in a vacuum, if you will.
yeah, I think it's certainly possible. So the next section is going to be on the CRM terrain. So if you think about terrain is like something like that, right? So I have one example where you have like one of those timer glasses with sand. Right?
Yeah.
So on the top, you don't have any motion, and the sand is like almost solid.
Mhm.
Then it starts flowing towards towards where the sand falls. And then when it's falling, they're individual particles without tension. So it's like almost like a gas. Like you have unlimited scope of expansion, and there is no force pulling the gas together. Right. So I think I've not read personally any papers that do it, but I don't think there's anything in the SPH theory that prevents you from doing it.
Okay.
The hard part would probably be imposing or defining the constitutive relation that makes this transition towards different phases. Like you want to know when it should behave like a solid based on external factors, when it should transition to a liquid, and when it transitions to a liquid, how it should flow. Yes. And once it becomes a gas, how it should expand. So that would be the challenge, I suppose. And I think with respect to like one thing that I'm worried about is like this SPH, like the weakly compressible SPH, right? So it's still weakly compressible in the sense that it's not incompressible, but it's also not gas-like.
Right.
Yeah.
Right.
So that is something that worries me, but I don't think that should be something that stops you from modeling.
Okay.
If you really want to speak someone who knows a lot more about SPH than me, the person who asked all this question, he's like one of the best SPH researchers in the world. Yeah. So a question like this, I gave you my opinion, but I think his opinion will also be very, very valuable. His name is Renato or something like that. But I don't know exactly what he's doing, but you should for sure talk with him, and he'll have a ton of insights, and he might also know some work that I've done.
Well, I appreciate your insights. Very.
Oh yeah.
Thank you very much. And also, when you the cursor application, we just downloaded that and started messing with it, and we're blown away.
Yeah, it's amazing.
We've been like kind of manually doing like copy paste in the chat to like the modification and stuff. But when we saw that, like, oh my god, it's just
Yeah. So I actually my plan was the last half an hour I would just mess around with the demo with Cluster
Yeah.
and show what it's capable of. I was just too tired. I guess. No man. But I might. Yeah, I might do it for the next one. But for Chrono, especially once you open the folder up, yeah, it has access to all those demos you could not. In my
we
opinion,
cloned the
not
repository and it was like, oh, it's like free.
So that helped me a lot in the past one year. I'm sure I probably.
Yeah, just like you said, the demos are gold. Copy paste as much as possible.
Yeah, yeah. I think that's the approach. I mean, personally, I genuinely do not know any of the APIs. I don't think it's worth remembering. So you just copy paste and
Don't need to reinvent the wheel on
it works there. Yeah. And going from if you have a high level idea of what you want to model, like in our case, just need to change a few parameters to get it. So, yeah. I hope you're. So what application are you supporting?
So we do SBIR. This will be related to water ice extraction.
Oh wow. Wow, that's good.
So David Group, who has done all that Viper work
Mhm.
with Rocha, I believe. You know, I mean that's why we're all coming here because we're just we use Project Chrono for phase one to do just granular mechanics of
Oh, I saw.
basically for the DEM. And now we're taking that to the next level of being able to try to use CFD coupling. When you guys released the email like a few weeks ago, show the simple heat transfer thing, you were because we've been messing around with like Star CCM on their DEM engine since it kind of has a little bit of that heat transfer stuff, and we were like, oh, do we need to connect like some stuff? Then we released that, we're like, oh, this is just way easier to since you already love Chrono.
Yeah. So that's the advantage of Chrono. You don't need to go very fast or simply. You can do a lot with just one software.
Yeah.
Yeah.
So we've been learning.
It's very cool.
Today, so.
Yeah, it's very cool. Your application is very fun. I hope you can simulate something.
Well, and it's the back technical point of contact with the company. So that's like it's cool to meet him too.
Yeah, he's always here for me. I'm really fascinated by him because he tries to run the code. I'm like, why does he need to run the code?
He just wants to get in the trenches,
Yeah,
I guess.
he loves the technical aspect. So yeah, I think that's it's pretty fun. All the best.
Oh, most definitely. Thank you. Tell you what,
Yeah.
let me give you. Can I give you? I have one back. I'll bring that back up to you.
Yeah.
It was a pretty near.
Yes, that's all. Well, yeah, that's great. Yeah.
Right now. I get instructions. That's
I think it's very